Equation migration RTM title. What we're going to do is going to take a very quick tour through migration theory. Of course, it discuss the evolution of models for migration, then how to derive Stolt pre-stack FK migration Green's theorem, and then how to do wave equation migration RTM. So we talked about wave separation from Green's theorem, and what this talk is going to be about is wave field prediction for migration. This is an entirely different attitude to the world from the talk right before. This talk is traditional, conventional kind of thinking, in the sense that it says that if you want the depth, you need the velocity. This presentation agrees with that. What we agree with is that this method needs the velocity. The method before is a different method, much different in terms of its use of information. And the way it uses the amplitude and time is very similar to the way multiples are predicted without subsurface information. So that's not this. So we went through this the other day, and we had an expression like 8, which is an expression for the wave field inside a volume from a volume integral over sources in the volume and a surface integral on the closed surface surrounding that volume. I cannot emphasize the importance of that, the words I just said. George Green said in 1826, if you want to predict what a wave field is inside a volume, you need measurements around, on the surface, around that volume. And that's been forgotten by a lot of people, thinking that somehow it's measurements on the surface that we have measurements on. So that must be adequate. Where's the theory that says you have a volume and you have surface, you have measurements on one side, and you can get a wave field predicted inside? The theory is that. That's the theory. That was the theory. That is the theory, okay, of how you predict a wave inside a region from measurements on the boundary and information about what's in the region. In early papers on migration, February 1978 Geophysics, two seminal work contributions, landmark contributions in one edition of Geophysics, Schneider's integral formulation for migration and Stolt's FK migration, in one journal. In Schneider's appendix derives from Green's theorem, Stolt's formula. Okay? So very related. But if you look at Schneider's paper, there's a picture like this, where the volume that they're predicting the wave inside of is an infinite hemisphere, where the medium is assumed to be known in that whole hemisphere. You can see a picture exactly like that. And some anti-causal Green's function that's works in that, that corresponds to that properties in that hemisphere with conditions on the surface which arrange it to vanish on the surface, excluding the need for the normal derivative, because it's a one-way wave. So you only need one measure. So with this anti-causal Green's function satisfying a zero condition on the measurement surface, Schneider and people who worked at GSI with him, who he references in the paper, derive an integral formulation for migration. And the surface integral, they argue, with an anti-causal Green's function, they argue that the lower boundary with an anti-causal Green's function in that second term in equation E, with G0 being G0 minus, but vanishing. In other words, this surface is that hemisphere. And they pick a G0, which is G0 anti-causal, and that vanishes on the measurement surface. So as not to need the normal derivative of the wave field, and argue then that the hemisphere, as r goes to infinity, that surface, that part of the surface's contribution to the wave field in the region goes to 0 at large r. So that says that the closed integral, they say, is the closed surface is equivalent to just having the upper surface, because this contribution will go to 0 with an anti-causal Green's function. Well, there are several problems with that model. One problem is it acts like you know everything. Everything is assumed to be known, the whole subsurface forever. And so there's no place for locating something that you don't know. You assume, and people made fun. At City Service Oil Company, people used to make fun of Claerbout, Stolt, and Schneider as saying those methods work great when you know everything. You know the subsurface, they'll give it to you. I remember distinctly hearing that kind of talk. So now that's one issue. Another issue is for an anti-causal Green's function. That Schneider is quoting on. The contribution of the lower hemisphere, as that radius of that hemisphere goes to infinity, its contribution to a point inside that volume does not go to 0. Goes to as far out as you go, it will produce a finite result. Causal, when G0 is causal here, you go far off, and Sommerfeld falls off. Anti-causal doesn't. So those two issues made a revision of migration model. Okay? Brought about a revision. And the revision is brought about the finite model for migration. The finite model for migration is much more satisfactory. It said you know a piece of the Earth down to some level, and below that you don't. And it's in that volume that you are seeking to predict a wave field. And you're looking to be able to predict what a source-receiver experiment would be inside that piece of volume where you know the properties. And then in some sense, you're searching for the onset of the unknown, the reflector. But you don't need to know the velocity below the reflector to locate the reflector. You need the velocity to the reflector. Yes? So, but that had another issue. If you have a finite surface, you don't have measurements at the lowest surface. The argument before, they try to just say it's far away, Sommerfeld, it doesn't matter. That's just not true with anti-causal. So the issue then, they said we're going to have a region where we know and a region where we don't know, but we just need to have enough information to be able to predict an experiment in some region to locate a reflector. So what are you going to do about the lower surface? So this is the finite volume model for migration. Well, it turns out And now you see, this is a one-dimensional version of that, where you have P grad G minus G grad P, and you have this Green's function, and we're making the piece of the region here homogeneous. Well, it turns out that if you have a finite volume, and if in that volume you have an upwave traveling, then if you pick the anti-causal Green's function, then that surface integral around that closed volume, where this is your measurement surface, and the lower surface of that volume is somewhere at depth, but not at infinity, some finite place where it's the boundary between you know and you don't know, yes? Then you can show analytically that the lower surface will give no contribution to the upfield as long as you're using an anti-causal Green's function. That the upper surface gives a contribution and the lower boundary does not. So you don't need it. That's for upwave in the region. So here's an upwave. If you pick an anti-causal Green's function like this, then you can show that the upper surface gives you the field and the lower surface gives you nothing. You don't need it. So an anti-causal Green's function, now for one-way migration, you just have an upfield, you should just need one measurement to predict the field at depth. So you get rid of the normal derivative term by arranging as Schneider did for the Green's function to vanish. So this is an anti-causal Green's function, and with this combination, it will vanish at some measurement location, measurement depth. And that D means Dirichlet. It's arranging to vanish on your measurement surface. And then if you take, this will then predict the field at depth from the upper surface in terms of data on the upper surface and the normal derivative of the Green's function, as George Green said. And if you take the derivative of this Green's function, lo and behold, you get Stolt shift. Just shift. How did that happen? It happened because this Green's function is essentially a shift divided by 2ik. And when you differentiate, the ik flies away, yes? And the 2 cancels because you have 2 of them that add up, it turns out, at that measurement surface. So for an upwave, an anti-causal Green's function for that medium will only require a surface contribution at the upper surface to predict an upwave. And it physically makes sense, because if it's moving up, then from measurements here, you are predicting in some sense the past. Where was it from where it is? If you pick G0 plus here, the lower surface will contribute, but not the measurement surface, because you're predicting the future. For an upwave, the future is that way, okay? From the bottom up. So, but since we have measurements on top, we pick anti-causal. And that's the relationship then between Green's theorem and the Stolt shift that predicts what a receiver would be at depth in terms of what a receiver is at your measurement surface for a homogeneous medium. So that's that. So one interesting thing is when you have a wave and you want to move it to another place, you don't multiply it by a Green's function. You multiply it by the normal derivative of the Green's function. There's often thought that you shift with a Green's function. You move. That's Huygens' thinking. Huygens, a long time ago, said if you have a front, a wave front, then every point on that front, every field point acts like a little source. And each of those sources produces a little sphere. And then you can, if you know which direction it's going, you predict the front nearby. That sphere is G0, so to speak. PG0. That Green, Kirchhoff and all those guys said that's not quite right. You need the field times the normal derivative on that surface to predict the field nearby. That normal derivative is what you take to make a field point act like a source to predict a field at another different point. Everybody understands? Huygens would have said G0. Yes? Just a sphere, isotropic sphere. Green's theorem says it's not isotropic. This has a directional difference. That's where all that obliquity comes from. Yes? Okay, so enough of that. So what about two-way migration then? In other words, as long as the wave is moving down to the reflector and then up from the reflector to your receiver, essentially anti-causal will do that job. If you have two-way waves, you have to start all over. If you have a wave that goes down and up, and then down and up, or if you have primaries and internal multiples in your data that you're migrating, which is not a one-way wave, okay? Then you have to start with what Green's theorem says. Now you say, I want to find a Green's function that will allow me to predict what a receiver will be inside that volume from measurements on top. Yes? That's the goal. In order to do that, you have to remove the contribution to the lower finite surface. To do that, you have to arrange the Green's function for that region to vanish along with its derivative at that lower surface. Okay? That will allow you to only use the upper surface. That's what we wrote some papers on, Bob Stolt, Jim Main, and myself, and JSE. I thought, it was just a way to do RTM without PML. Because you don't need a boundary condition, you have no contribution there. It was more than that, it turned out, because it was the first wave equation migration for RTM. Because what does it mean, wave equation migration? It means you predict what an experiment in the Earth for a receiver and a source anywhere in the Earth from surface measurements, and then make them coincident at time equals 0. That's the meaning of wave equation migration. That is one of the three imaging principles that Claerbout and his colleagues introduced in the 70s and the 80s. The other two, which is time-space coincidence of up and down waves and exploding reflector, are all three equivalent for a normal incidence plane wave. But as soon as you get a horizontal reflector even and non-zero offset, those three imaging conditions are not equivalent. Not. Time and space coincidence and up and down wave does not predict an experiment at depth, source receiver experiment. So what's so special about source receiver experiment at depth? What's special is if you have a reflector and you want to know whether it's there, where is it, and what the reflection coefficient is, nothing comes close to having an experiment right above it, where you have a source and you shoot, and you ask for small time coincidence. It's either is or isn't a reflector, number one. And two, you can get angle-dependent reflection information. That's because you have a source, you have an actual physical experiment. If you do some Kirchhoff imaging gives you candidates, gives you curves of possibilities. On this curve, it might be an image. Wave equation migration, when you predict a source and receiver experiment at depth, and you make them coincident at t equals 0, it's yes or no, there's an image or not. Okay? Not, these are possibilities, and let me get some more possibilities and see where they're ending up coherently and incoherently. They're in no way equivalent. And when you'll see the talk right after, with Chung Fu and Yang Zhao, you'll see analytically the difference between trying to get amplitude information from wave equation migration versus amplitude information from an asymptotic form of that migration, which corresponds to Kirchhoff. By the way, all RTM today is asymptotic. All RTM methods today bring the wave down, bring the receiver down, bring take your data down, take your source forward, and look for time and space coincidence of those two fields. That is not a source-receiver experimental depth. Not. Corresponds to Kirchhoff. So we will see in a one-way wave the difference that makes. So people like Yi Lo at Saudi Aramco, people like David Monk in Canada, they say, we don't really understand what that output of RTM is today. There are some people who say we can use it for amplitude information. We're not really sure what it means. So the talk that's going to follow mine will help understand what that means. So let me just show you what happens. This is the work of Fang Lu. We're just going to tell you this is, if you have up and down waves, meaning primaries and internal multiples, and you pick a Green's function that along with its derivative vanishes at some level, so that you only need upper measurements, then you can do a down continuation of your, now you can predict the source and receiver experiment and locate reflectors both above and below a reflector, above and below, and get not only structure but amplitude. This is for primaries and internal multiples in your data. There's a report that's in this annual report. We put it as an attachment because we provided it last year, that provides that. So there's a question about using multiples. People say we should use multiples. You know, we should be more holistic, have more diversity, free-range multiples, all kinds of things like that. Okay, free-range multiples, right? You don't understand free-range multiples? Stop mistreating the multiples. Okay. Okay. So the point is very simple for me. Why don't we treat multiples as signal? They have information. The reason is they have too much information. We can't decipher them. If you give me a smooth velocity, you have two choices. The velocity is either smooth or not smooth. Okay? Smooth means smooth. Not smooth means discontinuous. Okay? If you give me a smooth velocity and you give me primaries in any kind of multiple, free surface multiples, internal multiples, every multiple will give you a false image. Yes? So you say, okay, well, I'll give you discontinuous velocity. Well, you can't. That's the problem. We can't practically do that. We can't hardly do smooth. So the issue, the reason to keep multiples as noise is we can't treat them as signal. We can't give an adequate velocity. It isn't that we don't like them, it's they're too complicated. Their history, as this example shows. You could put primaries and internal multiples in your data and image, fine. But you better have that discontinuous medium. So if you feel confident at having that kind of discontinuous medium, not discontinuous medium, discontinuous accurate medium, okay? Then there's no reason. Multiples are just part of the wave field. George Green did not say only image primaries. He said image wave field. But he's going to tell you what kind of velocity you need to do that. Yes? And if we can do it, then we should. The issue for me is we have big problems, as we've said today, tough problems. And we feel we've made a little progress. We have tough problems with the multiples that remain that we cannot remove. Okay? They're not simple. You've seen progress, but we would be kidding ourselves to think that that's simple. why it's such a sensitive issue. We don't want to touch the primary, right? You got a multiple, so you sort of get it out, you don't get it out. But when you have it near a primary, the worst thing is to touch the primary. They'd rather leave the multiple there, yes? So there's a high ambitious thing we're after. If we start talking this kind of holistic talk, that multiples are our friends, you know, it isn't a personal thing. It's a practical thing. I'm happy to treat them as signal, but you better have that medium, okay? That's the message there. So with that set of positive words, I'll thank our sponsors for this talk and all the tolerance they have of these communications. I think it's important to have frank and forthright communications. And I appreciate the fact that you give me such strong support, and we have a growing number of sponsors, in spite of saying things that are not always politically correct. So I thank the sponsors for your encouragement and support, and I look forward to Chung Fu's next presentation.